2, 3, A and B. 2, 3, A and B. Continuity. Okay, so we're first going to talk about what it means to be a continuous function. Okay, now once again, yeah, what happened? Okay, continuous functions. We talked about this in ham or RAM, and basically there's a definition that says it's a function whose outputs vary continuously with the inputs and blah, 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 blah. It's very crazy, but the way that you want to think of it is this. If you have y equals f of x, okay, basically, in order to be continuous, that means that you can sketch the graph, I don't know if you remember this, without lifting your pencil. Sketch the graph without lifting your pencil. Okay, so think about things that are continuous. Polynomials are continuous. Whether you have, just a simple linear polynomial, just a line, or if you have a very complicated polynomial like that, that could be a 1, 2, 3, 4. That could be a 5th degree polynomial. Also things that have been continuous, the sine and the cosine waves, those are both continuous, okay? Whenever you have a domain of all real numbers, then your graph's going to most of the time be continuous. Not all the time, though. Not all the time. So I could show you one that has a domain of all real numbers and it's not continuous. Okay, so let's do one, and let's talk about this first one and all the different points of where this graph is continuous and where it's not continuous. So I want you to try to draw this graph as best you can. It is. You'll be all right. All right, so we have 1, 2. No, sure. Sure. And then we have 1, 2, 3, 4. Okay, and we're going to draw a weird piecewise graph that doesn't make too much sense, but so let's say we have a dot right here at 0, 1, and it goes to there and has an open circle, and then we have a dot right here which goes to 2, open circle. Let's put a dot at 2 above it, and then we will go up to here and down to here. Okay, so try to draw that as best you can. You could probably draw it better than I can because I'm not very good at drawing graphs on my iPad. Now they're going to ask you, in the homework tonight, they're going to ask you, A, to find the points where f is continuous. This is the graph y equals f of x. So they're going to ask you, find the points where f is continuous. Now, I like to really do the opposite. I like to find the points where it's not continuous. But the book's going to ask you this, so I want you to be aware. So this graph is continuous from, and it's always intervals of x, okay? So from 0 until you get to 1. So bracket around 0 to 1. Okay? Then it's continuous from bracket 1 to 2, and then it's also continuous from 2 to 4. Now remember, bracket means it's included, okay? Parenthesis means that it's not, and there it is. Okay, and that's what you write. Now for part B is a better question. Where is this graph not continuous? Not continuous. Well, it's not continuous wherever you see weird things happening in the graph. There is a jump at 1. We're going to talk about that kind of discontinuity. So it's not continuous at x equals 1 or x equals 2. And I don't like that. I'm thinking this shouldn't be a bracket here. I'm thinking it should be a parenthesis. I'm going to change that. Because how can it be continuous and not continuous? Yeah. So we'll go 1 to 2. Yeah. Right? Yeah, I'm sure you were thinking the same thing. I know. Okay, so in order to have continuity at a specific point, continuity at a point C. At a point C has to follow these 3 things. Okay? Here they are. Cooper, what are you listening to? Let's unplug. Let's be a part of this class. All right, number 1. He's listening to Screamo music.
Was I a shield? XXX tentacles.
Okay, here we go.
Is that the end of the problem?
That was it. Yeah. Okay, continuity at a point C has to follow 3 things. Number 1, the function must exist at x equals c. Okay? You have to exist there. That's kind of duh, right? In order to be continuous at a point, you have to actually have a point. So in other words, f of c has to equal some value b. Has to have a value. It can't just be a hole in the graph and nothing there. The second thing it has to do is the limit as x goes to c for this f of c point, or f of x value, has to equal something. Okay? The limit has to exist. It actually exists. Because, we have found sometimes that the limit does not exist at places. So the limit has to exist, the value has to exist, and the third thing is that the limit and the value have to be equal to each other. Those 3 things have to work in order to be continuous at a point C. Okay? So let's go back up to here and see how it fails at 1 and 2. So at 1, which one of these 3 things fails? Let's see. It has to exist a value at x equals c. So this one does have a value at x equals 1. The value is 1. Okay? So the first part checks. The limit exists. Does the limit exist at 1? No. Okay, as I'm going from the right, I get a limit of 1. As I'm going from the left, I get a limit of 0. So the limit does not exist. Okay, so it fails on the second thing, and it's not continuous there. Now take a look at x equals 2 now. At x equals 2, is there a point at 2? Yes, there is. There's a point, 2, 2. There's a value, okay? Does the limit exist? Yes. The limit exists. What is the limit at 2? The limit is 1. Both things are coming in here, right, like this, and they're approaching 1. Now the third thing says that the limit and the value have to equal. Does 1 equal 2? No, it doesn't. Okay? So this one passed the first 2, but not the third part. It has to pass all 3 parts in order to be continuous. Okay, so let's go ahead and...
Pass the first 2?
Yeah. There's a point that exists right here. There's our point.
How did it pass the second one? I thought you said that
The limit
didn't exist.
The limit does exist at 2. It's 1. Remember, they're coming in at the same, where are they both approaching from left and right? They're approaching the same y value. But those numbers, 1 and 2, are not equal to each other.
Wait, you said that the limit has an approach.
Two different points. I was testing x equals 1, and then I was testing x equals 2.
Oh.
Yeah. So x equals 1, the limit didn't exist. But x equals 2, the limit does. Sorry, I kind of put them all together, but I did it in different colors.
No.
I did. Red and yellow.
Doesn't count.
I'm sure I can send all this.
Okay. Part B. Now, so we're going to have graphs that are not continuous, okay? And there are 4 types of graphs, and you need to know them. So here are the 4 types of discontinuity. You learned 3 last year in pre-calc. And we didn't talk about the 4th one because it doesn't show up a lot, but this book does. Discontinuity. I really got to sound that out. There you go. 4 types of discontinuity. Probably the longest word I'll write today. Here they are. Number 1. I'm going to start with my favorite. Removable. Removable discontinuity. We saw one in that graph up above. The removable discontinuity occurred at x equals 2. Someone remove that point from there, okay? So an example of a removable, by the way, this is a hole in the graph, but its type of discontinuity is called removable. Some people will say hole, whatever. So here's an example of one. F of x equals x squared minus 25 over x minus 5. When you graph this, you know that the domain of this is all real numbers except x cannot be 5. Okay, you know that. If you plug 5 in, it's bad. So when you graph this, it actually just looks like a line. It looks like this. And at 5, there's a hole in the graph. You can't tell there's a hole in the graph, but a really good trick to do, which a lot of you guys did before, is you factored it, huh? You got x plus 5, x minus 5 over x minus 5. And you know what? I can remove it. Ah, bless you. Removable. It's a removable discontinuity at x equals 5. Hole in the graph. Okay, number 2. My second favorite is the jump discontinuity. Might as well jump. Go ahead and jump. All right, jump discontinuity. Think about a graph we've done already this year that went for a little while and then jumped up and went for a little while and jumped up and went for a little while and jumped up. Do you remember that one?
Always.
Yes, the greatest integer function. F of x equals the greatest integer of x. This one has infinite points of discontinuity. It happens at all of the golf numbers, right? The integers. You go like this, and then it jumps. It's called a jump in the graph. It's not a hole in the graph, but actually there's a space between the y values that it's equal to. They're very different, especially when you take limits, right? The hole in the graph, the removable, the limit exists here as I'm going towards each direction. This one, the limit does not exist. So they break different things, different rules that you had to be continuous. All right, number 3. Third favorite, infinite discontinuity. Infinite, I'm just going to abbreviate. I've written discontinuity too many times today. Infinite discontinuity, just a basic example, would be one of those rational functions like this. F of x equals 1 over x. Okay? There is a point of discontinuity at x equals 0. X equals 0 is the problem here because when you look at the graph, it goes like that and like that. There are vertical and horizontal asymptotes. And as you are approaching 0, it goes off to infinity or negative infinity or both. Doesn't matter. Okay, do you see the difference in all 3 of them so far? Don't get them mixed up. And here comes the 4th one, the new one for some of you. The 4th one is called oscillating discontinuity. Oscillating. These ones don't happen a lot. I think you've actually seen this graph this year, but we were talking about it as x goes out to infinity. We weren't talking about it at 0. So let's say f of x equals the sine of 1 over x. Now we know that x cannot be 0. We cannot plug in 0 for x. It's not in the domain. You get an error, sine of 1 over 0. You can't do that. So what's happening at 0? Well, this one is really interesting. I'm going to graph it on my calculator to show you. So let's say we have sine of 1 divided by x, and I hit graph. Look what it does here. Oh, that's weird. Okay, something happened in there at 0. So when I zoom in, you can kind of see it a little bit better. What it's doing is it oscillates between -1 and +1, but it never zeroes in. If you go a little closer, it goes up to +1. You go a little bit closer, it goes back down. So it just kind of jumps back and forth. So it doesn't have, they say it's not continuous there. It's not going to have a derivative there, what we're going to learn later. Okay? So it looks like this. It goes, what did it do? It just kind of went along here and it went like that. It goes up. Okay? There we go. So that's called an oscillating. So anytime you see a bunch of lines like that in the middle, that's an oscillation. Okay, so here we go. Let's do some. What number are we on? 3?
We're still part A.
We're on part B. Part 2? Part B?
No, it's
Okay, we're going to find the points of discontinuity and their type. Just did this in my ham class. They had to do the same exact problem I'm about to give you. He's doing just great. All right, y equals x squared minus x minus 6 over x squared minus 3x. Okay, well, you can graph it. Graphing's no problem. You can graph it, see what happens. I kind of want to, simplify this a little bit. I'm going to factor the numerator and factor the denominator. When I factor the numerator, I get what times what's negative 6 adds up to negative 1, negative 3, positive 2. And in the denominator, I can factor out an x. Factor out the GCF, x minus 3. Okay, so right away I know that there are 2 points that are bad, very bad points, right? The 2 bad points are x equals 0 and x equals 3. Now if you want to graph, you can, but if you just look at them, you can see that x minus 3 is what? Removable. Removable. And then you end up with x plus 2 over x, which is going to be an asymptote. If it doesn't divide out, it's an asymptote, so it's going to be infinite. And you can graph these if you want to. Go to y equals. Make sure you use parentheses around the whole thing.
Will we ever calculate on your class?
Yeah. Yeah, this is an AP. AP, they don't get their calculator on any quiz, I think.
Really?
Yeah, I was talking to some people. All right, so here's the graph. Calculators. See, if you look at x equals 0, you can see that it's an infinite. But then I look over at x equals 3 and I see no problem until I hit trace, plug in 3, there's no y value there. Y equals 0. Can you see that? Not really. There you go. Y equals 0. Y equals nothing. Not 0. Okay? So those are the 2 types for that one. All right, you feel pretty good? Do you remember learning that last year? You did. No? All right, you try this one. I'm going to give you a hard one. You can use your calculator. This is still part A.
Me.
No?
How many parts of it?
Well, it's letter
No,
B
it's
of
E
part A.
Yeah, that's
Okay, how many parts of it though?
No, we don't have much more to go.
How many parts is that?
I'll have to readjust. Let me give you one. You try this one, and then I'll tell you how many.
Okay.
Okay. All right. F of x equals x cubed minus 7x minus 6 over x squared minus 9. All right, you investigate this. I want you to answer a few questions. First of all, find what the domain is. Don't say it out loud. And then B, I want you to find the limit as x approaches 3 of f of x. And then I want you to say what the points of discontinuity are and what type. Bless you. Okay? And you can use your calculator. You can graph this. I'll pause. All right, so the domain of this function. Who can tell me what the domain is? All reals except perfect. Plus or minus 3. All right, so you got that. All reals except for plus and minus 3. We're going to find the limit as x goes to 3. What is that limit? Did you do it on your calculator? Yeah. Okay, you can't plug 3 in. And you probably don't know how to factor this. I mean, you know how to factor the bottom, but not the top. The top's a cubic, and it's weird. So if you hit trace and you plug in 3, obviously there's no value there. But we can plug in something very close to 3, like 2.999. And I get y equals 3 1/3. 3 1/3. Okay? So that would be the limit. Let's check from the other side just to make sure. 3.00001, 3.3 repeating, 3 1/3. Okay? All right, so the points of discontinuity are going to be at x equals 3, and the type that it is removable. That was a hole in the graph. And then at x equals negative 3, and that one was infinite. It's a lot like the last problem that we did. Okay, so then they're going to ask you, like, what would y be at the removable point? Y would equal 3 1/3 at that point to make it continuous. Okay? Let's go back real quick to
Okay, on the quiz, if we write asymptote instead of infinite, is it fine?
it's wrong. Yeah.
So it has to say infinite?
It's called infinite discontinuity. Yeah.
Yeah, roast.
For this one, let me go back to this one real quick. They might ask you in the homework, what would y be to make this removable point continuous there? And all you have to do is plug 3 in after you reduce. So y would be 3 plus 2 over 3. It would be 5/3. I think they're going to ask for that. I have a note to myself saying don't forget to mention that. Okay? If they ask you what y would equal in order for this to be continuous at 3, y would be 5/3. You reduce and then you plug it in. Let's look at this one. This removable. What would y be to make this continuous at x equals 5? Y would need to be 10.
Okay.
So once you reduce, you plug that number in and you get y is 10. So, okay? All right. So that was what? Part B. Let's move on to part C. Now here's the part where my dad and I like to argue over some stuff here. Because this really bothers me. All right. This is called continuous on an interval. So we just talked about that point, like f of x equals 1 over x has a point of discontinuity at x equals 0. Well, this says here that a continuous function is continuous at every point in its domain. Continuous at every point in its domain. Okay? And so if they ask you something like this, number 5, is f of x equal 1 over x a continuous function? The answer is yes. Okay? It has a point of discontinuity, but it's a continuous function. Right? The answer is yes. Okay, so take a look at the definition of a continuous function. The key part is at every point in its domain. And so when I look at 1 over x, the domain of this is all the numbers except for 0. So if they're asking me, where is this a continuous function? They're asking me, is it continuous on all the points that are in its domain? Yes, it is. Okay? 0 is not in its domain. So here's the graph. It looks like this, and it looks like this. Is it continuous at all these points that are not in its domain, that are in its domain? Yep, it is. Right? I hate that. Because it's like, I just said that that was not continuous at 0. But 0 is not in the domain, so we don't even talk about that. So it is a continuous function in its domain. Awful, right? I know, you hate that. I do too. Okay, last part. That was it. Part D. Composites. Composites are functions inside of functions. F of g of x, okay? F of g of x, g of f of x, functions within functions. Now it says that f of g of x is continuous. It will be a continuous function itself if f is continuous and g is continuous. Okay? If f is continuous and g is continuous. So you might not know what it looks like, what the graph looks like itself, or you might not get your calculator to find out if it's a continuous function. But if you know parts of it are, then it's going to be continuous. So let me go ahead and explain. Number 6. Okay, suppose that you have y equals the absolute value of the sine of x. All right. That's like two functions in one, okay? It's like saying f of x is the absolute value function, and g of x is sine x. Now those, you know those functions, right? You know the absolute value is a v shape. Is that a continuous function? Yeah. You know the sine wave. Is that a continuous function? Yes. Put them together, f of g of x, and so yes, this would be a continuous function. Okay?
I hear John whistling.
Great.
Can I call him?